Hello everyone. Today we'll be looking at CoolGAN, a GAN-based super-resolution method with a focus on perceptual realism. Single-image super-resolution is an important yet ill-posed image processing task, where the goal is to recover the original high-resolution images as best as possible from their downscaled and distorted low-resolution version. Why do we call it ill-posed? The reason is that even with simple bicubic downsampling, there are multiple high-resolution images that map to exactly the same low-resolution image, and the number of possible high-resolution images increases exponentially with the image size. A problem that arises as a consequence of this is that many super-resolution methods produce blurred images that lack finer details. Why does this happen? Because most of them, directly or indirectly, optimize for metrics such as peak signal-to-noise ratio and structural similarity. As has been pointed out in Pulse, minimizing the mean squared error, which directly optimizes peak signal-to-noise ratio, actually produces as its ideal solution the pixel-wise average of the set of all high-resolution images which downscale properly to the given low-resolution image. This leads to blurring in regions containing fine textures and patterns due to their high variance. We can see in this example that while the second image is quite sharp overall, grainy details from the water are smoothed out. So what are we looking for? Our goal is to consistently produce sharper, more detailed, and more realistic images. To achieve these goals, we propose a new GAN-based super-resolution method. Our generator consists of 5 main stages: shallow feature extraction, deep feature extraction 1, resolve 1, deep feature extraction 2, and resolve 2. The shallow feature extraction module consists of a couple of convolutional layers for low-level processing. This is followed by the first deep feature extraction module, where a bulk of the processing takes place in the 4 residual Swin transformer blocks. The structures of the residual Swin transformer blocks and the Swin transformer layers are as described in Swin IR. The Resolve 1 module upscales the image using a pixel shuffle layer and refines it with convolutions. Deep feature extraction 2 is another module where significant processing takes place. Although it consists of only a single residual Swin transformer block, the input feature map here has already been upsampled once. So the transformers in this block are acting upon a higher resolution feature map, which we believe contributes to fine details and structures. Resolve 2 upscales the image to its final resolution. CoolGAN is optimized using a combination of 3 losses: a pixel loss, an adversarial loss, and a perceptual loss. These are weighted by alpha, beta, and gamma respectively, which are updated as the training proceeds. We set a higher weight for the pixel loss initially to promote faster convergence, and then gradually level it off in favor of perceptual loss. The pixel loss is a simple mean squared error loss, while the adversarial loss is inspired by that in ESR GAN. The perceptual loss consists of the L1 losses between the feature maps produced by VGG and the Swin tiny network. This loss helps improve the perceptual quality of the generated images. We first perform a quantitative analysis against some state-of-the-art methods, where CoolGAN clearly lags behind in terms of both peak signal-to-noise ratio and structural similarity. But since our focus was on generating sharper and more realistic-looking images, we now inspect the visual quality of the images produced by CoolGAN. As we can see in these examples, CoolGAN produces images with sharper and more realistic details. Even in cases where interpreting finer textures is difficult, CoolGAN manages to generate realistic-looking patterns. Some of the drawbacks associated with CoolGAN are that while images contain greater details, they are also prone to containing more noise. Additionally, CoolGAN's results can only be demonstrated in terms of perceived visual quality and cannot be quantified. We hope to improve upon these in future work.